and reducing nitrogen leaching under intensive vegetable production in temperate regions. What you can see here in the background in the first slide is a picture of the Lake Horofenua in the lake where I work. Now, I'm going to outline a little bit how the vegetable farming in New Zealand works. It has a low coverage with around 0.5% of the total national agricultural area. Despite this, it can leach around 120 kilograms of nitrogen per hectare per year, although this is not very well documented and more studies are needed. The main vegetable crops can be divided into fresh and processed, with the main ones which you can see here. And it is considered one of the most leachable land uses in agriculture in New Zealand. So this is the Horofenua catchment. This is the town of Levin, and right next to it is the Lake Horofenua. And this is the Arafata subcatchment, which main land use is the vegetable farms. And at the bottom of the catchment in dark blue line is the Arafata stream, which is the main tributary for the Lake Horofenua. In the past, the Lake Horofenua has been subjected to several interventions, such as direct sewage from the town of Levin to the lake for 35 years. What you can see here are two satellite images from Google Earth. On the left one, it's from 2005. And the right one, it's from 2011. And there's clearly a progression of cyanobacteria blooms. And what is thought that can be the main cause of this is the intensive vegetable farming around the catchment. So nowadays, the Lake Horofenua has more than 4 times the maximum allowed of nitrogen for this kind of lakes. To cope with this situation, the Regional Council has established maximum cumulative nitrogen amounts, and this has taken by surprise to growers of the area, and they often don't know how to cope with this. So in order to help these growers to meet this criteria, we are exploring here different in-field and edge-of-field strategies that can potentially reduce the nitrate leaching. So the main objective of this research is to identify and assess through field trials and modeling the performance of a range of in-field and edge-of-field farms strategies to reduce nitrogen leaching from intensive vegetable farming in Arafata subcatchment. So the first component is the water monitoring around the catchment. For this, I selected 9 points around the catchment from top to bottom. And I monitored nitrate, ammonia, and I also did a qualitative flow monitoring. So you can see here in the left the levels of nitrate and ammonia concentrations. And it is possible to notice that there's not much contribution from the top of the catchment, except from the drain number 3, right here. And the main concentrations are mostly in the bottom. Then the point number 8 is actually the Arafata stream itself, and the point number 1 as well. So you can see that the levels of nitrate before and after, there's quite a big jump of nitrate. So this is qualitative monitoring of flow, and with this, I would like to highlight that from the 100% of times that I went to visit these drains, only around 37% of these drains were flowing, and the other ones were not flowing. So with this, I'm trying to say that most of these nitrate concentrations are from stuck water or from stagnant water rather than from flowing water, even though the sampling was made after intense rainfall events. This is a survey that Horizons Regional Council did for boreholes during 1985 and 2001. And it's around 21 boreholes that were monitored. And we can see several of these monitors that contain high levels of nitrate. And so from this study, I calculated the mean, and it goes around 6.6 milligrams of nitrate per liter. So it is possible to notice that groundwater concentrations of nitrate might be quite high. The second component of this study is in-field trials. For this, I selected two fields, one at the top of the catchment and one at the bottom of the catchment. The one at the bottom of the catchment is green vegetables, and at the top is mainly potatoes. For the green vegetable side, it has an area of 0.15 hectares and is mainly a silt loam series with imperfectly to poorly drained and slow permeability. The treatments here are control with no fertilization, a standard practice, which is the practice that the grower has currently, an excess practice, which is the double of the amount of fertilizer that the grower applies, and a chicken manure that follows the same amount of nitrogen as the standard practice. Here we can see a layout of the treatments. It's mainly 4 blocks and 2 repetitions. And the treatments have been disposed in a randomized complete block design. In the paddock, there's a small area of lysimeters. There are 20 lysimeters. It's the same for treatments, but with 5 repetitions. And for the potato crop side, the area is 6.7 hectares. And the difference of the soil is that this one is moderately well drained. The treatments were no fertilizer with and standard practice with the same amount that the farmer applies, control release fertilizer, and liquid fertilizer. So all of these ones were following the same amount of nitrogen than the farmer applied, and these treatments were also disposed in randomized complete block design. So we can see here some previous results, preliminary results of the potato side. The standard practice was the one that had the highest yields, followed by the control released, and the worst ones were the liquid fertilizer and no fertilizer. Despite this, we can see here the soil nitrate in the first study and the 30 to 60 centimeters. And in both of these graphs, we can see that the standard practice is the one that had the most nitrate in the soil, and the control release fertilizer had one of the lowest ones. The third component of this research is the calibration and validation of APSIM model. From these field trials that I just described, I will do simulation of in-field practices to reduce nitrogen loss across a range of crops and soils. And we can see here a short an overview of how APSIM works. And so this works with several scripts and management scripts, and also this is the calibration for the soil. And several graphs can be displayed and at the same time. So this is something that makes APSIM quite unique. And the fourth component is the calibration and validation of SWOT model. So from these APSIM simulations, plus drainage and groundwater sampling across the catchment, I will perform simulation of nitrogen leaching across the catchment and the use of edge-of-field practices to reduce nitrogen losses. This is an example catchment from SWOT Plus, and so from this picture, I would like to highlight that this will help to identify the best placement or where would be the most efficient place to reduce nitrogen leaching in the catchment. So as a summary, at catchment scale, nitrate contribution from surface drains is generally low. Most likely, nitrate pathway is through groundwater rather than surface water, mainly because these drains do not transport high amounts of water in even in intensive rainfall events. And for the infield, alternative practices may help reduce nitrate leaching in vegetable farming systems. Thank you very much.
Hi. Okay. Hmm. Okay. Excellent. Not sure if that's good or bad, but great. Great. Thank you very much. Have a great day.
I'm Megan, and today I'll be presenting some research we did investigating the release dynamics of enhanced efficiency nitrogen fertilisers, or EENFs, in a subtropical field environment. This research was for my final year honours project for my Bachelor of Agricultural Science at the University of Queensland. So the main issue we were addressing in this project is the fact that nitrogen use efficiency remains quite low in cropping systems, and this is largely due to a lack of synchrony between the supply of N to a crop and crop N uptake patterns. So farmers typically apply their nitrogen towards the start of the season, but while the crops are still quite young, they're not really using much of this N. And in the meantime, it's prone to a range of loss processes that make up the nitrogen cycle, which means that by the time your N uptake is reaching its maximum, only a small portion of the originally applied N is actually available for the crop. Obviously, from an economic perspective, this is not ideal, as the money you're putting into purchasing and applying these fertilizers is not being realized in your crop. But the loss of nitrogen from soil back into the environment also poses quite a large pollution concern, most notably nitrous oxide into the atmosphere. It's quite a potent greenhouse gas, and also the leaching of nitrate into waterways to cause algal blooms and all those sorts of issues. So there's certainly a lot of motivation to optimise nitrogen use efficiency in cropping. And this is where enhanced efficiency nitrogen fertilisers come into play. So these are a range of technologies that have been highlighted as one potential solution. It's a broad term. There's a few technologies that fall within it, but they all do aim to improve the synchrony between N supply and crop N uptake. In this project, we were looking at two. So our first one was our nitrification inhibitor, and it works by conserving your fertilizer as ammonium. So it's temporarily stopping the conversion of ammonium to nitrate. And this is based on the premise that ammonium is much more likely to stay in your soil for longer compared to nitrate, as nitrate it's quite mobile in the soil, and it's also prone to loss back into the atmosphere. Our second type of technology were these controlled release fertilizers, and these work by releasing N gradually into the soil from these granules, which are coated in a non-soluble permeable substance, mostly plastic. And unlike conventional fertilizers, where all the N you apply is immediately present in the soil, it is instead released gradually and is based on the premise that this better matches your N uptake by your crop. This is all well and good, but experiments to date investigating the performance of these products have mostly been in very controlled environments, i.e. glass houses and labs even, and there is still an overall lack of evidence regarding their performance in field environments. So that's exactly what we set out to do. Our aim was to investigate the release dynamics of 5 contrasting EENFs in relation to a standard fertilizer, so granular urea, in a subtropical field environment. We had 5 different EENF products. We had 2 polymer-coated CRFs, 2 plant oil-coated CRFs, a nitrification inhibitor, and then we also included granular urea as a conventional N fertilizer, so we could compare these technologies back to that. And we also had nil plots, which allowed us to quantify any background soil and dynamics throughout the experiment. This here is just a montage of our experimental process. So we applied all our fertilizer in subsurface bands, about 10 centimetres below the soil surface, and all our fertilizer was applied at the same rate, which was 150 kilos of N per hectare, which is quite a mid-range rate to be using. And then at 5 points throughout our experiment, we dug holes in every single plot and took a variety of soil samples from each plot. So on the band, above the band, below the band, and lateral to the band. And then we took these soil samples back up to our labs, and we firstly extracted any intact CRF granules we recovered, and we set them off for analysis for their N content. And this allowed us to quantify the rate of nutrient release from our 4 coated products. And then for every single soil sample we took, we did a 2 molar KCl extraction, and this allowed us to quantify the concentration of urea N, ammonium N, and nitrate N on and around the band for each product through time. And in a nutshell, this is what we found. So this series of graphs represent the net fertilizer N, so urea, ammonium, and nitrate, that we recovered in our soil sampling zone for each product through time. We have accounted for any background N while doing these calculations. So this is just the fertilizer N. And across the board, you can see that there was a fair bit of variability in the nitrogen dynamics we observed for these different products, which does suggest to us that there were a variety of mechanisms through which these products are working. I'll step through the key findings in the next couple of slides, but I'd just like to point out for our granular urea, we did see this nice decline in the concentration of fertiliser N we were recovering in our sampling zone through time, whereas for the other products, it varied. So our nitrification inhibitor, for example, a much less gradual decline, and then our CRFs all did display to some extent a gradual release of N. So at 7 days, there was relatively less N, and then through time this increased, and then it decreased again once this N was in the soil and prone to transformation and loss. So our first key finding was that the nitrification inhibitor, so our DNPP urea, did prolong the persistence of ammonium in the soil, and that helped to conserve the amount of N in our sampling zone. So these graphs here are made from the exact same data set as that previous image, except we've converted it to mass, so milligrams, and we've also depicted the 3 forms of N, so urea, ammonium, and nitrate. And you can really see, firstly, the decline was much more gradual for the DNPP urea compared to the granular urea, and we can also see that relative to our standard granular urea, the ammonium was the ammonium made up a large proportion of the amount of fertiliser and we were recovering for our DNPP urea through time. This is particularly evident at 46 days. So for our NI treatment, more than half was still ammonium, whereas for our granular urea, it was probably less than a quarter. And because our ammonium is so much better held in our sampling zone, it's attracted to the clay colloids in the soil, meaning it can't be leached out of our sampling zone. It's less likely to diffuse beyond our sampling zone, and it's also not prone to loss via denitrification. It was staying in our sampling zone and we were recovering it. However, as the experiment progressed, the inhibitory effects of this chemical wore off. An increased proportion was converted to nitrate, and then it was subsequently lost from our sampling zone. All our CRFs were found to release the N gradually, but there was some variability between these products. As you can see in this graph, nice curve through time, bit of variability. This data does have quite a few limitations though, so we were obviously only able to recover any intact granules that we recovered in the field. So any that had burst to release all their N, we wouldn't have found, wouldn't have analysed. So this may have actually underestimated our true N release. But having said that, based on our visual assessment of these granules, we did see some differences in their mechanistic behaviour in the field, and this was largely consistent with supporting literature from previous studies, which suggests that granules can either rupture and release all their N at once, or they can swell up really nicely and release the nutrients gradually via diffusion. And we saw that in our plant oil-coated products. So the only difference between these two products is the thickness of the coating. This one is a lot thinner, this one is thicker. After 46 days, these had all ruptured and released all their N, and this was consistent with our soil data that we also obtained. Whereas this more thickly coated product was able to withstand the swelling, released its N much more gradually. You can see this granule is still intact. And again, this is what we saw in our original soil data as well. So that is a very good example of differences in the mechanistic behaviour of these granules and the resultant impact that this has on the N dynamics we observed. So up to this point, we've established that these products did display an array of release dynamics. But across the board, we did find that these technologies all meant that more N was recovered in our sampling zone later in time. And this does suggest a potential for increased synchrony between N supply and demand, linking that back to what I was saying right at the start. Crop N uptake at the start of the season is quite low. However, as we do progress towards maturity, this uptake does increase. So if we have more N available later, when the crop is using more of it, it does suggest that perhaps a greater proportion of all the N we've applied will actually be utilised by the crop. Having said that though, we still need to be considerate of the timing of application. This is not a magic fix. We still need to know when in time our crop's going to be needing that N, so we can then work backwards to know when best to apply these products. This leads me on to the big question though, can EENFs actually improve NUE? So Obviously, I said that we do have potential for increased synchrony between supply and demand, but some questions do still remain. So we only looked at one soil type and one set of environmental conditions. As these are the key drivers of N dynamics in the soil, we do need to have an understanding of these products across a range of conditions. Similarly, we only looked at one form of placement, so we only and applied these products. So if there's any interaction between how we use these products and how they work, we wouldn't have noticed that. And more broadly, there's still some gaps in terms of the understanding of the actual role of fertiliser N and crop N uptake. And I think until we really finesse that understanding, the extent to which we can predict how these products may solve low NUE is still quite limited. But other than that, that's pretty much what we found. I normally ask if anyone has any questions, but obviously this is pre-filmed, so I hope whoever's watching this has enjoyed it and hopefully learned something.
Hey Megan, at this stage there's no questions via the app, but
Yeah.
we'll keep you on for a couple more minutes and just see if anything comes through.
Okay, right, too easy. I've got a question in there asking about the soil type. It was a black vertisol, I think.
Yeah, so what soil was used in the field study?
Can you guys hear me?
Yep.
Yep, so it was a black vertisol.
Thank you.
Do you mean like untreated and treated, like the fertilizer, or what do you mean? I guess if you're talking about using a combination of perhaps, there's a really big delay, enhanced efficiency nitrogen fertilizer, normal ones, that might be an option just because they are so expensive. So you might want to be using them where you think that there might be quite a high N loss potential, and maybe not using them if you don't think there's going to be much risk of you losing a lot of N.
Awesome, thanks Megan. That's a wrap with the time now, so thank you.
Thank you.
Appreciate it.
Okay, see ya.
Can I start? Yep. Okay, so good afternoon, everybody. My name is Naoya Takeda, a PhD student from QUT in Brisbane. This presentation is about responses of fertilizer 15N recoveries to nitrogen fertilizer rates in a tropical sugarcane systems. As you know, sugarcane is a big, important rural industry here in Queensland, and it's often intensively managed with high nitrogen input. But on the other hand, it has is it on? Should be on? Yeah, it should be working. To where?
Left, right, really? No?
Sorry, 1 second. I'll go to the next slide.
Okay. Yeah, well, it's intensively managed, and it has been raising concerns about nitrogen pollutions. As you know, like we've got Great Barrier Reef right next to sugarcane production regions, and it is estimated that 46 to 65% of the total dissolved inorganic nitrogen load is attributed to sugarcane systems. And also, sugarcane systems account for more than 25% of the fertilizer-derived N2O emissions in the entire Australian agriculture sector. So we have to account for these environmental impacts of nitrogen losses into the nitrogen fertilizer management strategies. Well, traditionally, we are aiming to maximize the yield, and we are looking at the responses of yields to nitrogen rates. But to account for those environmental impacts, we have to know the responses of nitrogen losses to N rates. But then how can we get this response in the, from field experiments? One way is to use the 15N labeled fertilizer. By using this 15N fertilizer, we can track the fate of the nitrogen fertilizer into the crop nitrogen uptake and into soil nitrogen, and then by the balance of these three, we can estimate the amount of fertilizer 15N loss. But these 15N are usually pretty expensive and also requires laboratory analysis and with facilities, so the studies are not this very abundant yet. In case of sugarcane, it's commonly ranging from 20 to 40%. And then in Brazil's cases, they applied different nitrogen rates and resulted in the similar fertilizer nitrogen uptake efficiency. But they didn't observe the fertilizer nitrogen remaining in the soil, so we haven't investigated the response of these losses. That's why this study investigates the effect of fertilizer nitrogen rates on fertilizer 15N balance, all of these three components in an intensively managed sugarcane, tropical sugarcane system. Here's the materials and methods. We conducted a field experiment on a commercial sugarcane farm in Ayr, Bardakin. The site had a dry tropical climate and brown dam soil with the soil properties listed here. In the experiment, we had 4 nitrogen rate treatments, 0, 150, 200, and 250 kg nitrogen per hectare. And in this site, for this site, 200 was the recommended rate. And the experiment had 4 replicates, and then each of the plot had micro plots of 2-meter section. And for this 2-meter section, we applied 15N labeled urea fertilizer. And regarding the crop management, nitrogen fertilizer was applied by 2-sided banding, and the sugarcane was managed with furrow irrigation and also barn trash management. And just before the farmers harvest, we sampled plants from the entire 2-meter section for the total biomass and trash amount, and then we separated it into tops, stalk, and dead leaves, and then like we coarse ground coarse grinding and drying to measure the dry-fresh ratio. For the soil, we took soil cores down to 1 meter at 4 points from bed center to furrow center, and then each of these 1 meter soil core was split into 4 layers to see the distribution of nitrogen fertilizer in the soil. And then these plant and soil samples were further dried, ground, and analyzed by IRMS, which is the equipment shown here, to measure nitrogen content and 15N enrichment. Then fertilizer 15N amount was calculated by the mass balance method. Here are the results and discussions. Here's a fertilizer 15N uptake, and it's shown as a percentage, so it's efficiency. And we also compared with the apparent method, which is just the difference from the control plot. In 15N method, we didn't see any response of fertilizer nitrogen uptake efficiency across N rates. And then it was a lot lower than the nitrogen uptake efficiency by the apparent method. This was because in the fertilizer plot, soil-derived nitrogen uptake was larger than the control. And then in the apparent method, this increase was counted as fertilizer nitrogen. So by using 15N, we can accurately estimate the contribution of nitrogen fertilizer to crop nitrogen uptake. And then we didn't see the response in this fertilizer 15N uptake or in the sugar yield either. So these results indicate the native nitrogen, native soil nitrogen supply might be a bit higher, and thus nitrogen fertilizer requirement can be potentially lower than the current assumption to sustain sugar yield. The next result is the fertilizer 15N remaining in the soil. As you can see, across N rates, the distribution was very similar, and then it's mostly recovered in the topsoils. Down to 20 centimeter, it was 55% of the fertilizer 15N recovered, and then down to 40 centimeter, it was more than 70%. And then the absolute amount of across profile, it was between 36 to 39 kg nitrogen per hectare. So this indicates the limited capacity of the soil to immobilize nitrogen fertilizer. And then increasing nitrogen fertilizer rates did not contribute to the increased retention of soil nitrogen. And by the balance method, we can see the fertilizer 15N losses. As you can see, there was a positive response of fertilizer 15N loss to the N rates, and also the proportion is shown in brackets, and as you can see, the proportion was also increasing. So if we apply more and more nitrogen fertilizer, basically it's not going to the soil in plant, yes, increase, but in terms of the efficiency, the ratio, it didn't increase. And then it went to the losses, to the environment. So environmental costs and then agronomic inefficiency basically increase at higher nitrogen fertilizer rates. So these are the results for the fertilizer 15N balance, but I'd like to expand this result a little bit with other preliminary results, particularly focusing on the loss pathways. We also measured N2O emissions as well, and then N2O emissions increased exponentially in response to N rates. And also we had our incubation study for these soils, which is shown in the poster session downstairs actually. And then we observed the high N2-N2O ratios. Combining these findings, we can estimate the large fertilizer nitrogen losses via denitrification. And sorry to forget, but also we didn't see the clear evidence of nitrogen leaching in the fertilizer nitrogen recovery in the soil either. So that also supports this hypothesis. And then we also had a similar experiment in Mackay. And then now we are, it's still preliminary results, but we are trying to see the relationship between nitrogen use efficiency and N2O emissions. Here we plotted N2O emissions, which is scaled by sugar yield, against nitrogen surplus. Surplus means the difference between N rates and crop nitrogen uptake. And the right-hand side, we plotted against fertilizer 15 and uptake efficiency. So these N2O emissions basically increases exponentially to the nitrogen surplus and decreases with fertilizer 15 and uptake efficiency across two sites. So these findings support the idea that excess of nitrogen fertilizer over crop nitrogen demand can explain the non-linearity of the response of N2O emissions. Conclusion, so we saw like over 50% of applied nitrogen fertilizer was lost even at the recommended rate, and it can be mostly via denitrification. And also the capacity of the soil to immobilize nitrogen fertilizer was limited. And then we also saw the large amount of native soil nitrogen removed by the crop biomass. So potentially, these two factors cause the long-term soil nitrogen deficits despite the high nitrogen inputs. So basically, avoiding the excessive nitrogen fertilizer application should be the priority to reduce the environmental impacts while enhancing nitrogen uptake efficiency simultaneously in sugarcane systems. And a little bit of the future work. So we've been working on the denitrification losses by 15N gas flux method in field and incubation both. Combining all these results, we are trying to quantify the losses via denitrification. And also, to avoid the excessive amount of nitrogen, we have to estimate the amount of nitrogen supplied by the soil, which means estimating mineralization. That requires further extrapolation of these field experimental results by crop models. We've been working on it with APSIM, and then we are trying to understand better of these nitrogen cycles and to suggest sustainable nitrogen fertilizer management strategies in sugarcane systems. This is all for my presentation. Thanks very much. If you got any questions, just ask me or hit me up. Yes?
How much fertilizer left over after 2 rows? So you found out that 50% of fertilizer
yes.
was gone after you harvest your sugarcane, but how much left over after 2 seasons?
After 2 seasons, unfortunately, we didn't continue at the same site, so we are not absolutely sure about the carryover effect. But it's typically only like less than 5 kg of nitrogen is taken up in the following season from other studies' results. So we estimate the carryover effects to this following season is quite low. And it's often the contribution from the previous season is more coming from the residue. And then in this particular site, they had trash burning management. So the nitrogen in the biomass was mostly lost either as well. Yep. Okay. Yeah. Thanks very much.
Hello everyone, sorry I couldn't be in the conference in person. So my name is Shala and I'm from Griffith University. I'd like to acknowledge my collaborators, particularly Rachel, who mastered the DNA metabarcoding for root species identification. And this was a very exciting project that I worked with her and I enjoyed it. Okay, so this study was undertaken in Papua New Guinea, where coffee and cocoa are two main cash crops, and they also need a shade tree. So within the project, a shade tree was Canarium trees. Canarium indicum is a rainforest species, and it is an indigenous species in Pacific. And also, it's a timber tree. But the bonus of this species is that it produces edible nuts. Within the project, we commercializing the Canarium nut. Watch the space is going to be exported to Australia late this year or next year. So the bonus is that because it produces nuts, the farmers can have additional income every year in addition to what they gain from coffee and cocoa until the trees are mature and they can harvest them for timber. So the shade tree species and spacing regimes are really important for a successful agroforestry systems. Within a previous project, we found that the optimum spacing regime for this specific tree species with cocoa was 8 meter by 60 meter. However, in the previous study, we didn't find any significant effects of these Canarium tree on soil nutrient availability for cocoa. So we hypothesized that because they develop a complementary rooting systems, that's why they live happily next to each other, especially if we get the spacing regime right? So you know that the study of roots are always challenging. So for example, if you dig the soil and take out the roots, and if the roots of those species are not very distinctive, you can differentiate which species are those fine roots, right? So we needed to, and this was a case for the fine root that we collected from cocoa, coffee, and Canarium, the fine roots. We couldn't say which species they were. So we developed a DNA metabarcoding for root identification. And the main objective of this study was to see how the root of shade tree and cash crop develops in the soil profile using metabarcoding, and also how they are affecting soil nutrient availability, whether these three being next to each other would affect the Canarium nut or cocoa bean quality. So this is a photo of the Canarium nut. As I say, watch the space. It's going to be exported late this year or next year. So we collected the root and soil samples in the soil profile up to 80 centimeter. And then we analyzed the root samples using metabarcoding, and then we analyzed soil, cocoa bean, and Canarium nuts for their nutrient concentrations. So our hypothesis was confirmed. We found that for example, cocoa trees, they have more root abundance within 0 to 30 centimeters. You can see here the brown area is the abundance of the cocoa trees. And then when you are going deeper in the soil profile, you see more abundance of the canarium roots compared to cocoa trees. And it was the same story under the canarium trees. So when you're going down in the soil profile, you could see more root abundance of the canarium. Same story was confirmed with cocoa roots and coffee roots when they, canarium roots when they living next to each other. So the main finding was that these root metabarcoding worked for species identification, which was very exciting. And then we looked at the soil nutrient concentrations under cocoa, coffee, and canarium. And practically we didn't find any significant differences at each soil depth. So it means that soil nutrient concentration wasn't really affected by the presence of canarium trees next to either cocoa or coffee trees, which was a really nice finding. When we looked at the cocoa bean and canarium nut concentrations, so the majority of nutrients in cocoa beans were higher than the same nutrient in canarium nuts. So it suggested that the nutrient accumulation wasn't really in cocoa beans, wasn't really affected by the presence of the canarium trees next to those ones. So here it is a potassium concentration. You can see it was higher in cocoa beans than canarium. And calcium, it was a little bit different. So the cocoa trees next to canarium, they didn't differ in terms of the calcium concentrations, but those ones planted a little bit far away from canarium, they had significantly higher calcium concentrations than canarium nuts. So the conclusion was that yes, our hypothesis was confirmed, and it was really good to see these shade trees living happily next to the cash crops without affecting the cash crop in terms of soil nutrient availability, also nutrient accumulation in the beans. So at the end of the day, it's because they developing complementary rooting systems. So it means that when you are harvesting beans or canarium nuts, still in terms of nutritional value, they haven't been compromised if you are eating it. So it is a bonus when at the end of the day, you don't want to have a food that in terms of nutrient has been compromised because of we didn't get right in terms of how we can plant them in our plant mixed species planting systems. Well, thank you very much for listening to this presentation. And as I said, I'd like to acknowledge the funding body for this project, which was ACIR. Thank you very much.